Okay, welcome back. We're picking up today with a new unit on properties of sound and electromagnetic waves. We're going to start off with sound, and then we're going to be moving on to electromagnetic energy, which includes light and all the other energy we use for radio waves, Bluetooth, Wi-Fi. It's all part of the modern world. So we've been on this theme of energy, and we started off with the unit on energy, and we talked about the various kinds of energy, which included electric energy, wave energy, sound energy, nuclear energy, chemical potential energy, talked about the renewable sources, and talked about the non-renewables. So we've been on this energy theme, and this unit continues with that theme on energy. Electromagnetic energy is particularly important, and so is sound energy in the 21st century. So we're trying to understand basically how our world works today. So we're going to take a look first at this clip on energy and motion, and we're going to look at the 4 types of waves to review.
Light waves from the sun and also the radio waves that carry radio and television signals to us are examples of transverse waves. Sound travels to us through compression.
Notice how the speakers are popping in and out, forcing the air to compress right in front of the cone of the speaker. When it pulls back, that makes the rarefaction.
Compression waves. Earthquakes produce both compression and transverse waves, but are commonly referred to as seismic waves.
Seismic waves are combination or surface waves.
The 2 types of waves travel at 2 different speeds and have different effects on buildings and the crust of the Earth. While seismic waves travel through the Earth and sound waves travel through the air and various other materials, electromagnetic waves travel through electrical fields. For this reason, electromagnetic waves, like light, are the only waves that can travel through the vacuum of space. We can see these astronauts performing work in outer space, but we would be unable to hear them in space as there is no medium through which the sound of their work can travel.
Remember, sound is a mechanical wave. There needs to be particles for the compressions and the rarefactions. In space where there are no particles, there would be no sound. A sound wave is a form of energy that travels in longitudinal or compressional waves. Like all waves that we said in the last unit, it starts with a vibration. So like your vocal cords vibrate, the strings on a guitar vibrate, a resonator in an instrument vibrates. Because a sound wave is a mechanical wave, the vibrating object collides with the air molecules, and when it pushes onto the air molecules is what causes the compression. So they transfer energy from one molecule to the next molecule, like we learned in the last unit on waves in general. So as the compression bumps together, it pushes the energy along through the medium. The vibrations push the air molecules together at the compressions, and then as it vibrates back, it spreads apart at the rarefactions. So here, our example of a compressional wave is usually a spring. Sound waves and springs, work the same way. So we've looked at a couple of examples of slinkies, and this tight together part is the compression, and then the spread apart part is the rarefaction. So most of this should be reviewed from what we learned in the last unit. And eventually, when the wave energy stops, the molecules return to their normal or rest position. Now, here I have a picture of a compressional wave. And if you can imagine this red thing over here, this is like a speaker cone pushing in and out, or something vibrating like your vocal cords, or anything, the head of a drum. When it pushes out like this, it causes the compression. And when it pulls back, it causes a rarefaction. And the same thing with a speaker. So there's this little animation of this speaker, and when it pushes out, it sends out the dark rings, which represent the compressions, and then the light rings represent the rarefactions. And so I put it here next to, it's going to this ear, and the compressions travel along through the medium, until they would hit your ear, and that causes a vibration first on your eardrum, and that's how we hear. Okay, so we know that sound waves are mechanical waves, which means that they need a medium and they need matter to travel through. So, the matter can be solid, liquid, or gas. Okay? And this type of wave is a mechanical wave and it needs a medium. Sound travels faster through solids than liquids and then gases, okay? And then it travels not at all in a vacuum. So as the medium becomes less dense, the sound travels slower. And eventually, in a vacuum, it doesn't travel at all. So a lot of times in science fiction movies, in outer space where it's the vacuum of space, the space battles, we hear a lot of sounds and it's exciting and whatever. But there is no sound in space. So as we just said, when the atoms are closer together, like in a solid, the atoms collide faster and they're easier for them to get into the compressions because they're already close together. So sound goes fastest in a solid. So sometimes in a Western movie, you'll see somebody put their ear to the ground or their ear to a railroad track. That's because the sound travels faster through the ground or the railroad track than it does through the air. So you would be able to hear it first. Also, the temperature affects the speed of sound. As the temperature increases, sound travels faster. And this is because what we learned about in the kinetic theory. As you heat something up, the atoms are moving faster because they have more energy. They're more able to move and get into the compressions and into the rarefactions. You can think of something that was really, really cold, particles would have very little energy and it would be hardly moving. So it'd be really difficult for them to get into the compressions and into the rarefactions. So that atoms moving faster so they can bump and collide faster. Now the amplitude of a sound wave is just like the amplitude of a compressional wave that we learned about in the last unit. And it's really the difference between how tightly packed the compressions are compared to how loose the rarefactions are. The bigger the difference between the two of them, the more energy the sound wave has. So as we said before, the tighter the compressions, the more dense they are compared to the rarefactions, the more amplitude or energy the sound wave has. And I put in here, the greater the difference between them, okay? So it's, high amplitude sound waves have really dense compressions and very loose rarefactions. And then we're gonna take a second look at the video I made about the amplitude of a longitudinal wave. Okay, this is a short clip I made to try and demonstrate the amplitude of a compressional wave. Now notice when the spring is pulled back, there's definitely some differences between where the compression is down here and where the rarefaction is. Now there's not a big difference between the compression and the rarefaction. So as we said in the notes, this should have smaller amplitude. Now notice in this case, the compression is very tight and the rarefactions are loose. So there's a big difference between the compression and the rarefaction. So we said amplitude of a compression wave depends on the difference between the two. So in this case, these are very tight compressions and loose rarefactions. And as you can see, there was a lot more amplitude. Now, in this case, I grabbed the spring from about the same position. There's definitely a compression and rarefaction, but the difference isn't as great. So we would expect that it would not have as much amplitude. Now in this last example, I am going to make a very tight compression and there'll be a big difference between the rarefactions. So this one should have the most amplitude. Okay, and as you can see, the compression is very tight, and because I grabbed so much of the spring, the rarefaction is very loose compared to this compression. And it had so much energy, so much amplitude that it went to the other end and it bounced back. And you can see that the spring had a lot of power. Now, sound intensity is how much sound is flowing through an area in a certain amount of time. And the way we perceive that is loudness. So, if there's a whole bunch of sound in a small area, we say it's very intense. So I put in the notes, loud sounds are more intense and quiet sounds are the opposite. So you have to be careful with this. Sound intensity can damage your hearing. Now, obviously, sound is used for music and for singing and making sounds, warning signals. So this is where we come into thinking about pitch. And pitch is how high or low a sound seems to be. And that's really determined by the frequency or the number of wavelengths that pass a point per second. So the frequency is determined by the vibrations per second. So something that has a real high frequency, like a cymbal or a flute or a piccolo, but it'd be emitting a lot of vibrations per second. Increasing the frequency means a higher pitch. And these are higher sounds like cymbals or a flute. Ultrasonic sounds are above human hearing. So they're above, we can hear to about 20,000 hertz or about 20,000 wavelengths per second. After that, we can't hear. Frequencies lower than that means it's decreasing the pitch of the thing. And this would be like a bass or a bass drum that you'd hear or a subwoofer. These would be the low frequency sounds. Subsonic sounds are below what we can hear. They're below 20,000 hertz. Dogs and some animals can hear sounds above what we can hear, and some can hear sounds below what we can hear and sense those low rumbling sounds. So notice that the sounds are labeled based on our hearing. Ultra sounds are ultrasonic, and we're going to talk about ultrasound. Those are the sounds that they use for imaging. So they're just sounds above what we could hear. So, and subsonic are sounds below what we could hear. We're going to stop here and we're going to pick up here next time with the Doppler effect.